Today we're going to go ahead and finish up Unit 1.5, and I hope that we finish early enough with you for you to have some time to work on the homework. So let's get right to it. I dropped my sign. It's from Ashley Green. She made this for me last year. Anyway, guess what? As it turns out, you can use a table of data to figure out what degree a polynomial is. So far, you've learned how to do that for quadratics, and the way that you recognize quadratics was you found that the change in the average rate of change was a constant value, and I was calling that delta AROC, right? So if the change in the average rate of change was a constant number, then you had a quadratic on your hands. But what if it's not a quadratic? Well, it turns out that you could still use the table and you could still use basically rates of change. But rather than call them rates of change, what we're going to do is we're going to call them differences, successive differences. And you can only use successive differences to identify the degree of a polynomial if the x's are equal length intervals. So because the change in x is identical every single time, I'm allowed to use the successive differences. And what that means is figure out how you got from one y value to the next. I'm going to do this in different colors. So instead of calling it the average rate of change, which it is, it's the average rate of change. But instead of calling it the average rate of change, let's call it the first differences. This is the average rate of change. To get from negative 30 to negative 14, I'd have to add 16. To get from negative 14 to negative 12, I would have to add 2. Oh, hey, check that out. It didn't change. Significant. From negative 12 to negative 2, that's plus 10. From negative 2 to 30 is plus 28. And from 30 to 96 is plus 66. Since these are the average rates of change, wait, you have a question for me?
Yeah, so what you just read is the average rate of change, is the y value average rate of change?
These are the actual y values of our polynomial.
That's all I
Yeah, these are actual y's. So this being the difference in the y's over equaling input values, the difference in the y's is also the average rate of change. So you can call it the first differences, or you can call it the average rate of change. So what do we have here? Yes? What did I say, 28? Yeah, I added the two numbers, didn't I? There you go, plus 32. Thanks. The good news is it wouldn't have changed my statements that I'm about to make, but it is good that the math be right. Alrighty. To the left of this, what I have are positive rates of change. Can someone raise a hand and let me know what a positive rate of change tells me about my curve? Well, you're whispering, but if not, hold on. This is average rate of change. So I have positive average rate of change. You're thinking of the change in the rate of change. Don't worry about their values. Worry about the fact that they're positive, and that's all you need to know. Do you need a shout out? Do you need a shout out? Yeah. He needs a shout out. Help him out. It means this graph is increasing. Now, since you were talking about concavity. So because these numbers are positive, I have a positive rate of change, I know I'm increasing. Now, plus 16, then plus 2, then plus 0. Because the amount I'm growing is falling, again, because the rate of change is decreasing, would that be concave up or concave down? This is concave down. So what do I know just from looking at this? My graph is increasing, but it's concave down. Once again, positive rates of change, my graph is increasing. But if you look, this number was getting larger. So my rate of increasing is increasing. Concave up or concave down? Concave up. Right here, I have a rate of change that is 0. That means at this point, probably at negative 0.5, I have a flat point on my graph. To the left of it is increasing concave down. To the right of it is increasing concave up. That is going to force the curve to look like this. Increasing concave down, flat, increasing concave up. And right here was our inflection point at negative 0.5. But it was increasing across the entire thing. I knew all of that just from those blue numbers and analyzing what I see in the blue numbers. All right. This has not told us what our polynomial's degree is. It just told us the behavior. Just by knowing that piece of my graph looks like this, though, I can guarantee that this thing is not a second-degree polynomial. Because second-degree polynomials, quadratics, do not have inflection points. Question for me, or are you scratching your nose that way? It could be a cubic, but we don't know that it might come back down over here. All you see is cubic, yes. But that was just based on what I have here. Let's say the table kept going. For all we know, it does drop back down. For all we know, it drops back down and then back up. That's just what we have right here. So on this interval, I know that is an inflection point. That's what I know. Yes?
Why is the inflection point there?
The reason why I'm saying it's probably there is because this flat piece happened right here between 0 and negative 1. Yep.
So, like, it's degree can't be even.
It could still be even, because what if it comes back down? Then it would be even.
Okay.
It could be. We don't know. This is what we know right now. It looks like that on this space. Great. Let's find our second differences now. By the way, second differences, up until now, I've been calling that the change in the average rate of change. Let's make our lives easier. Let's all know that it is the change in the average rate of change, but let's just say second differences. Make our lives easier. Okay? From 16 to 2 is minus 14. See how my change in my average rate of change is negative? That's how I knew it was concave down. And then from 2 to 0, minus 2, see, concave down. Because my change in average rate of change is negative. My rate is decreasing. Okay? Now from 0 to 10, that's plus 10. Ooh, we're concave up again. 10 to 32 plus 22, staying concave up. 32 to 66, excuse me. 34, still concave up. It's important that you know that these numbers are lining up with the negative 2, with the negative 1, with the 0, with the 1, with the 2. So this did not tell me anything I didn't already know. I already knew I was concave up to the left of this number and concave up to the right of this number. We knew that. But it reinforced the fact that this can't be a quadratic because the second difference is the change in the average rate of change was not a constant value. It reinforced that idea. Third differences. Third differences do not tell us anything about the curve itself. All the curve's properties, increasing, decreasing, concavity, inflection points, turning points, all of that stuff is found in the first two differences. Okay? So everything after this is just us trying to find the degree of the polynomial. Negative 14 to negative 2 is plus 12. Negative 2 to 10 is plus 12. 10 to 22 is plus 12. 22 to 34 is plus 12. Since third differences is a constant value, polynomial is degree 3, which is a cubic. So now we're guaranteed that it was a cubic. This tiny span of numbers with just this image from the blue and the red was not enough to confirm cubic. Yes?
So if it only like became the same on the fourth difference, it would be
Of fourth degree, yeah. So if it took us to another line to get all the same value, then it would have been a fourth degree polynomial. A couple other things that we need to understand. Because this rate here was a constant number, that makes this rate linear. This is a linear rate because it's growing at the same amount each step. So because this one is constant, this one is linear. So when we were doing the stuff with quadratics, if the second difference is a constant value, you have a quadratic. That's the same thing as saying if the rate of change is constant, you have a quadratic. That's the same thing as saying the average rate of change is linear. You see, there are all these different ways of saying the exact same thing. And we have to understand why they're all the same thing, because the AP exam questions are going to be word heavy. And did you understand the implications of the words? All right? You'll never be able to just mimic what I'm doing. It will never be successful. Yeah.
So just to recap, if I did 5 differences and then finally got a constant and moved to the 5th degree?
Yep, if it took you 5 differences to get the same number over and over and over again, then you'd have to say that it's a 5th degree polynomial. Which would mean that the 4th differences were linear. Which would mean the 3rd differences were quadratic. See? The first differences would have then been 3rd degree. You know, they step up each time by a degree. Cool beans? Not cool beans. Zach, do you have a question for me?
we just keep going until you get all the same.
Yeah.
No matter.
Yeah, you keep going until the number's exactly the same.
Is there ever like a situation where it will never all be the same?
Yes, tons of times, but not for polynomials. For every polynomial, what we're doing works. Are there math functions where this never works? Of course there are. You know why? Because they're not polynomials. What we're doing right now is when you're looking for the differences to be the same, that trick only works for polynomials. The other functions have different patterns, and we'll use those, we'll figure those out along the ride throughout the year. Yeah, Max? So you find the change in the last change until you get a constant number, yes. Yeah?
This is like a bad question. Like, what's like the definition of a polynomial?
Okay, a polynomial is a thing that's held together with pluses and minuses, where all of your x's have exponents that are whole positive numbers, or 0. So no radicals, no x's in the bottom of a fraction. They have to be whole exponents or 0, and they must be positive. That's what makes it a polynomial. All right. Boop. Let's do some graph sketching. We're going to write a polynomial function of minimum degree, meaning make it the smallest degree possible. And we know that the front number is a positive number, which is nice, they told us. And we need to include these zeros. We know that x equals -3 is a solution with a multiplicity of 2. It's a repeated root. We know x equals -1 is a solution, and we know x equals 4 is a solution, and they are both multiplicity 1, meaning not repeated. So f of x equals, if -3 is a solution, then x plus 3 is the factor. Multiplicity 2 means there's an exponent of 2 there. If x minus 1 is a solution, then x equals -1, excuse me. If x equals -1 is a solution, then x plus 1 is a factor, multiplicity 1, so degree 1. And if x equals 4 is a solution, then x minus 4 is a factor, degree 1, because multiplicity of 1. The front number on mine is a 1. I don't need to write it, which is a positive number. This is a polynomial of minimum degree with those properties. You would need to FOIL and do the distributions and all that stuff and combining like terms to figure out what this polynomial is. I mean, the x plus 3 squared would get you x squared plus 6x plus 9. And then the last two would multiply to be x squared minus 3x minus 4. Then, of course, you'd have to do all 9 distributions and combine all your like terms. I'm not going to waste our time. Since this is an AP classroom, I'm going to assume that you can all do that. It gets us x to the 4th plus 3x to the 3rd minus 13x squared minus 51x minus 36. There. Part A is complete. Now part B wants us to fill out this table. That would mean you'd have to plug all these numbers into your polynomial. Ew. I really don't want to do that. I'm going to let the graphing calculator do it for me. So I'm going to show you how to do that. I think I've already showed you before, but I'm going to show you again. But before I grab my technology, I'm pretty smart. So are you. And you already know what several of these numbers' values are in here. At x equals negative 3, it's a solution. So the y value, 0. X equals negative 1 is a solution. So at negative 1, 0. And x equals 4 is a solution. So at 4, 0. And if you throw in x equals 0, negative 36. There. So I know those 4 numbers without doing any work. Well, without plugging in. I mean, I already did some work, but there it is.
How did you get negative 36?
I plugged in x equals 0. All of those things would have turned to zeros. Handy dandy calculator. Go to y equals and type in the polynomial. Or if you don't want to type it in like this, type it in like that. Shoot, that's probably even easier. Let's do that. X plus 3 parentheses squared, x plus 1, x minus 4. Look how fast that was. That was much faster than typing that junk out. So like I said, I'm going to let the calculator do this work for me. I am not going to be plugging in these numbers. That's too much work. Instead, I'm going to go to the table of data for this equation. See that blue word that says table? You got to hit the blue button to make that thing do its job. Second graph, there's the table of data for you. You don't have to type anything else in. All the numbers are there. Here's the x's, here's the y's. So when x is negative 4, y is 24. When x is negative 2, y is 6. 1 comma negative 96. And 5 comma big number. Wow. I'm finished with the graphing calculator now. Time to sketch this graph. And it is going to be a rough sketch. And I mean rough. Okay? Because what we really care about is its overall behavior. Where things are occurring as far as increasing, decreasing, positive, negative, that kind of stuff. Right now, all we're really going to care about is above the x-axis and below the x-axis. If you want to know increasing, decreasing, or even worse, concavity, well, you're going to have to work a lot harder. Then you might have to grab the calculator, do second trace max, second trace minimum, things like that. We don't care a lot about that. Let's see what we got going on. I know I have 0 at negative 3, negative 1, positive 4. We'll graph in green. Green feels good. Green for good. 0, 0, 0. At negative 4, which isn't even on my graph, but if I go out to negative 4, I'm up, right? And at -3, what's my graph going to do since I've got a multiplicity of 2? Bounce. So I know at -4 I was up here, and I know I'm going to bounce off of x equals -3. So the graph is going to do something like this. Okay? It's going to bounce off of this number. I know at -1 I'm at 0 again, but if you look at -2, I'm at a nice positive number. So it clearly went up and then caved back down. Didn't have a choice because that's a positive number. At 0, I'm at a pretty colossal negative number. Okay? At 1, I'm extremely negative number. There. That's good enough. Good enough. Got to bounce here, cross here, cross here. If you want to see the actual picture, oh, my window's bad. Window, let's go my y minimum to -150, my y maximum to 50. Let's go by, yeah, sure, why not? Wow, I went to -150 and still don't see the bottom. Okay. Now, I won't make it onto camera, but I'm going to switch over to Desmos so you can see the actual graph. That's the actual graph. And if you wanted to see the critical values for it, you could click on it, and you could see that I had to go all the way down to -158 and change to get to that minimum value. But my sketch has the overall shape. It's close enough, right? Close enough. Okay. Especially to do parts D and E, because it says on what intervals is the graph f of x greater than 0. What that means is, when are your y values positive numbers? And this one says, when are your y values negative numbers? So when are my y values positive numbers? Well, that means you're above the x-axis. When am I above the x-axis? To the left of -3. So the question is, would it be brackets or not? Let me ask you, if you're on the x-axis, what is your y value? 0. Is 0 greater than 0?
No.
Nope, so you cannot put a bracket there. You're once again above the x-axis from -3 to -1.
So when is like the correct time to use brackets?
When is the correct time to use brackets depends on what kind of question you're asking. Because there's lots of different times when brackets are appropriate. I mean, I could list them all for you if you'd like.
Like specifically for this one, like.
Well, never for positive negative. Unless it's an end point. Let's say that the graph comes to an end right here at my thumb. Okay, this point would forever be above the x-axis, so it would be forever positive, so bracket there. But you can't put brackets when the graph is crossing through the x-axis, because at the x-axis, the y value is neither positive nor negative. It is once again positive, though, after x equals 4. If we were doing increasing, decreasing, every time you found a turning point, so there'd be a turning point here at -3, there's a turning point somewhere between -1 and -3, there's a turning point somewhere between -1 and 4. At every turning point, there'd be brackets for increasing and decreasing. Concavity, though, never gets brackets, though, for the same reason why this doesn't get brackets. So it's just domain sometimes has brackets, are there endpoints. Range sometimes has brackets, is it a global maximum or a global minimum? It really just depends on the setup. And below the x-axis, from -1 to 4. There it is. You did this in Algebra 2. Well, you were supposed to. If you were with me, you did it. This is the same thing as saying, when is f of x positive, when is f of x negative? It's the exact same thing. When is f of x positive, when is f of x negative? And on to the back. This whole positive-negative business, again, you would have learned it in Algebra 2, and you would have used something called a sign diagram to solve for it. particularly with polynomial inequalities. Here we have a polynomial. It is a third degree polynomial. I know because 1, 2, 3, that's the exponents. 1, 2, 3, so this is a third degree polynomial, so it's a cubic. And I can see that my graph hits the x-axis at -3 and +4. That's when f of x equals 0. Like that. What we're going to do here is we're going to put our two zeros, known as critical values, on a sign diagram, or a sign chart, sometimes called. I prefer sign diagram. And we use a sign diagram because we are literally going to be looking for pluses and minuses. That's what we're looking for. I only have two critical values that go on here. Those two critical values are -3 and +4. Picture not drawn to scale because who cares? Okay, there it is. -3, +4. There are three zones to this graph. There's numbers to the left of -3, numbers between -3 and 4, numbers to the right of +4. What we are going to do is we're going to pick a representative from each zone and mentally substitute it in and ask ourselves, did I get a positive result or a negative result? I would like to point out, though, it does not matter what you plug into these parentheses, because you can't plug in 4. What kind of values are going to come out of this set of squared parentheses? Say it louder for me, Gavin. Positive only. Because everything squared is positive or 0, and it only happens to be 0 if you use 4, and we can't use 4 because it's already here. So everything I plug in here, I'm going to get a positive result. In fact, because I know that, I'm just going to go ahead and put a little plus sign in parentheses for each one of these zones, and we're going to get another set of parentheses and put a symbol in those as well. And then we're going to ask ourselves, when we multiply those two kinds of numbers, what do we get? Cool. A nice representative to the left of -3 is -4. If you put a -4 right here, this set of parentheses is negative. The product of a negative number and a positive number will always be negative. So I already know that to the left of -3, my graph has y values that are negative. I already know to the left of x equals -3, my graph is below the x-axis. Next zone happens to have my very favorite test number. Between -3 and 4, somewhere in there you're going to find the number 0. I love testing 0 because it's freaking easy. 0 plus 3 is positive. The product of two positive numbers will always give you a positive result. So between -3 and 4, I have positive y values. Between x equals -3 and x equals +4, my graph is above the x-axis. And then pick any number to the right of 4. It doesn't matter what you choose. 5 is a great number. 5 plus 3 is positive. Product of two positives will always be positive. Oh, so I'm also positive after 4. Ta-da. Yep.
You wouldn't use brackets.
We can't use brackets on positive and negative because at the number x equals 4, we're on the x-axis, which is a y value of 0, which is not positive, nor is it negative. Okay. Is that a question?
No.
He raised his hand and pointed at the screen and said, chicka chicka.
No, never mind.
No, never mind.
I was going to ask something and then I just
Figured it out?
yeah.
Okay.
So we're only using x plus 3?
No. Plug in anything you want to these parentheses.
Any of the parentheses?
No. You're plugging it to everywhere.
Oh.
But you see there's two, I have two things here. That's because there's going to be two results. There's going to be whatever this result is, and then this result. But this result will always be positive because it's squared.
Oh, okay.
So I just didn't bother because I always knew that that was going to be a squared result, which means that was always going to be a positive result.
I can plug in any number.
Plug in, give me a number.
5. -5.
-5. -5 plus 3 is negative. Negative 5 minus 4 is negative 9, but you square that, you get a positive. It's out here. A negative number times a positive number gets you a negative value.
Oh, times.
It's a product. This is multiplication here. Your OK says no.
I never learned this in science class.
Last year? Who'd you have?
Mr. Victor.
Wasn't honors. That's why. No, but it's because that's not an honor standard. I mean, that's not a algebra 2 standard. That's why. Okay? That's why. But are you cool with what we're doing? This is the x-axis. And all we're doing, you know what? Let's draw what this graph would look like.
So whatever you plug into the equation, that value, you times it.
You know, I'm plugging it in to every x, and I'm looking to see if I got a positive result or a negative result. So we know that this graph crosses the x-axis at negative 3, and I'm just going to, this is quick and painful, okay? And we know it crosses at positive 4, but specifically, we know it bounces at positive 4. So this is a positive cubic, and all positive cubics have this look to them, ish. They have a positive average rate of change, right? So I know I'm going to cross through this number, and to bounce off this number, I have to go left, down, right, up. It forces my graph to look like this. It doesn't have a choice. And if you look, everywhere to the left of negative 3, I'm under the x-axis. Between negative 3 and 4, I'm above the x-axis, and after 4, I'm above the x-axis again. So what a sign diagram does for us is it tells us what kind of y values we have without telling us the actual y values. It's just a fast way of knowing if you're above or below the x-axis. That's all it is. Which has huge implications in calculus. Big time important these things are in calculus. Yes? What's up? Start off with all positive. Okay, so here, okay. We're plugging in an x value to here and here. But since this thing is a squared set of parentheses, every number that comes out of here is a positive number. Think about it. 10 minus 4, 6. 6 squared, positive. Negative 1 minus 4, negative 5. Negative 5 squared, positive. So all I was saying was I'm going to figure out what this number's symbol is. And if this was a negative, it's negative times positive. If this is a positive, it was positive times positive. That's all we were doing. Let's do it again. This time we have a polynomial inequality. Okay, well, you could, if you hate yourself, try to graph this and this and figure out where this cubic graph is below this quadratic graph. And it really is a darn shame that Desmos won't make it onto the camera here because I happen to have those two curves on Desmos. There they are. And if I could zoom in a little bit too so you get a better image. So what we'd be doing if you really hated yourself was try to factor both these things, try to graph both these things, and figure out when the cubic, which is the thing in blue here, again, it's not on camera, is below the green thing. And we're going to do all of that using algebra instead of graphing it. Okay? The way that's going to work is factoring. But we don't try to solve by factoring ever until one of the sides has a 0 on it. And you want your biggest exponent thing, you want that term to be positive. So since this is the largest exponent and it's already positive, I'm going to move everything towards it. It's like the magnet, it brings everything close. So I have to subtract the 4x squared, I have to add the 16. It's going to give me x to the third minus 4x squared minus 4x plus 16. And we need this cubic polynomial to be less than or equal to 0. See, I just brought everything away from the right, so it leaves a 0 over there. I subtracted the 4x squared and I added the 16. Because we haven't reviewed the rational root theorem and Descartes' rule of sign and all that stuff, we don't have to use that here. it must be able to factor by grouping, and it does. It factors by grouping. Thank goodness. So, artificially group the front two things and the back two things, being very careful to capture that minus sign in the second group. In my first orange group, I need a GCF, x squared. And in my second orange group, I must have a GCF. And because it starts with a negative number, that GCF is negative. Sometimes it's just the number -1. This isn't one of those cases. These two things have -4 in common. It'll leave behind x minus 4. And, oh good, x minus 4. You see, if those two orange parentheses hadn't had the exact same stuff inside, I would not be able to solve, or I wouldn't be able to factor by grouping. But since they match, I can get away with it. I put the two orange things together by factoring off the x minus 4 from both orange objects. It leaves behind an x squared minus 4. And lastly, x squared minus 4 also factors. It's the difference of two squares. It is a squared minus b squared. The difference of two squares will always instantly factor to conjugates. A plus b times a minus b. And just because I like the order better, the two orange things, I'll put them first. X plus 2 times x minus 2. Then I've got the purple thing, x minus 4. And I know the whole shebang needs to be less than or equal to 0. Before I go any further, are there any questions on the factoring by grouping? Everybody's comfortable with all that. Sweet. There are 3 critical values because there are 3 different numbers that will have this thing equaling 0. Those 3 numbers are whatever makes the inside of the parentheses equal 0. So x equals -2, x equals +2, x equals +4. This cubic polynomial has 3 zeros. That means none of them have multiplicity 2. That means every one of these is a place where our graph goes through the x-axis, no bouncing here. Let's put them on a sign diagram though. -2, +2, +4. Picture not drawn to scale. There are 4 zones to check. And what we're doing is we're taking a representative from the zone and we're plugging in bang, bang, bang. Should be 3 symbols, and all 3 symbols are being multiplied to each other because, you know, these parentheses are all touching. So this is a product. Any number to the left of -2 will work, like -3. -3 minus 2, or excuse me, -3 plus 2, that's a negative number. -3 minus 2, that's a negative number. -3 minus 7, that's a negative number. 4, yeah. Oh, it's because I did -3 minus 4 is -7. But it's a negative number. The point is, we have the product of 3 negative numbers. What kind of result will that give us? A negative number. Great. Any number between -2 and +2 works. My favorite representative happens to reside in there, 0. 0 plus 2 is positive. 0 plus 2 is negative. 0 minus 4 is negative. Now when you multiply those 3 things, you're going to get a positive result. Yes?
If it can't bounce, if you just got the first one, could you just do it? Like it's just interchanging.
This man has graph theory knowledge. Yes. Since we can guarantee this polynomial can't bounce and we know it's crossing through the x-axis all 3 times, it is guaranteed that it will oscillate between the 2 words over and over and over again. Yep, absolutely. But for good note-taking purposes, I'm going to show me testing zones. But yes. Number between 2 and 4, 3 works. 3 plus 2 is positive. 3 minus 2 is also positive. 3 minus 4 is negative. Womp womp. One negative number gets you a negative product. And then lastly, any number to the right of 4 like 5. 5 feels good. 5 plus 2 is positive. 5 minus 2 is positive. 5 minus 4 is positive. The product of those 3 positive numbers gets you a positive result. Let us get our solutions from this. What we did was we brought everything to one side. And if you care, this thing is called the related polynomial. That's just the words that is. This is also the same thing. This is the related polynomial. It says, when is this polynomial less than or equal to 0? It doesn't say less than 0. It says less than or equal to. So how is that going to change our answers? Brackets now, because it says or equal to. Less than is negative numbers. So this zone works. And this zone works. Because of the equal to bar. So that gives me negative infinity up to negative 2. Bracket, union, bracket, 2 to 4. Bracket. So are there times when you use the brackets for this kind of stuff? Yes. It just depends on the situation. Graphically, if you wanted to know, negative 2, positive 2, positive 4, we know it crosses all 3 times, and we know, just like this one, that it is a positive cubic, so it has this left down, right up shape, and it crosses through all 3 of these. It forces this kind of image, like that. Doesn't have a choice, and our solution set has not changed. It is still that, but just so you can see what's going on, I'm going to break out the yellow pen, because I rarely use it. Here is my graph being underneath the x-axis, and here is my graph being underneath the x-axis. And that, fellow nerds, is all she wrote.